behalf of the Ivan Board of Directors, I'd like to welcome you all to our next Ivan workshop on application of DFT calculations in NMR spectroscopy. I am going to now pass it over to Krish to give us some more information about their next upcoming meetings.
Thanks, Eric. I'm supposed to be Dave Rice today, but I'll be both. I wanted to talk about, before today's meeting, I'm going to announce what is coming down the pike in the Ivan workshops. Next month, that's in August, 29th of August, last Thursday, we have a panel discussion on the topic of advanced MRI and MRS applications in brain and liver. It will be led by Professor Arya Nishaja at University of Memphis. She will be joined by 2 panel members. You should receive the invitations soon after this month panel discussion is complete. Coming down the pike in September, the week after the SMASH conference, we are going to broadcast the Ivan board meeting, which we call it a fireside chat by Ivan, which was recorded so that we can be transparent as well as solicit ideas and support from the greater Ivan group, worldwide Ivan group. So look forward to that as well in September. And we are working on a few more topics down the road. So with that, today's panel discussion is on application of DFT calculations in NMR spectroscopy. It will be led by Alexei Buevich for Merck, and he will be joined by 3 members of panel. I will let Alexei introduce the panel and start the meeting. Alexei, it's all yours.
Thank you, Krish. Thank you for this kind introduction. So good morning, good afternoon, good evening. So because we are in different time zones, let me share the screen first. Okay, welcome to our webinar on the application of DFT calculations in NMR spectroscopy. My colleagues, Ryan, Cohen, and I have the privilege of serving as the chairs for today's session. We have a very exciting lineup of the speakers. They will share their expertise and insights on past, current, and future applications of the density functional theory in NMR spectroscopy. Because of the vast range of applications of DFT and NMR, it is almost impossible to cover them all in one webinar. Therefore, today we will focus solely on application and solutions, and perhaps the applications for the solid state could be covered in a different webinar session. So before we begin, I would like to briefly introduce our distinguished speakers and the topics they will be discussing. Firstly, it is a great honor to have with us Professor Dean Tantillo from University of California, Davis. Dean and I first met a decade ago when we co-chaired a workshop at the SMASH conference on the same topic, and the same that we're going to be discussing today. So his exceptional work at that time, as well as the subsequent years, along with the highly popular among the DFT practitioners, the website that he created, Share NMR, they actually speak for themselves, and he doesn't need additional introduction. So Professor Tantillo has graciously agreed to set the stage by introducing the concept of DFT. So he will also share practical recommendations and examples of DFT applications in synthetic and biosynthetic chemistry. Our second presenter is my colleague, is Dr. Ryan Cohen. I must admit that Dr. Cohen is the primary driving force behind DFT applications at Merck. And actually, he is not only limited to the NMR applications of DFT. Those applications are going far beyond the NMR. But his explorations of DFT methods are both comprehensive and thorough. And they found numerous practical applications in our daily work, which is we are focusing on design and synthesis of potent pharmaceuticals. Dr. Cohen will be sharing his recent findings on the calibration of the DFT predicted chemical shifts by taking into account additional factors that have not been explored before. It is a truly fascinating story. The third and fourth presentations will focus on the combination of DFT with other methods. I will provide a brief overview of the role of the DFT can play when combined with another powerful method called computer-assisted structure elucidation, also known as CASE. This combination of the two methods has the potential to improve structure elucidation protocols of small molecules, making them more robust and more efficient. Last but not certainly least, we have the honor to hosting Professor Craig Butts from University of Bristol. His laboratory work on developing structure elucidation methods is widely known beyond the UK. Particularly because of his achievements in combining DFT with machine learning algorithms. And that will be a topic of his presentation today. So throughout the webinar, we highly encourage active participation from all attendees. Please feel free to ask questions, share your thoughts, and engage in fruitful discussions during the Q&A session that we are planning after the presentations have been done. Without further ado, we are now invite our first speaker, Professor Dean Tantillo, to begin his presentation. Thank you and enjoy the webinar. Dean, please take it away.
All right, well, it's great to be here. And so I'm going to give you kind of a brief introduction to using DFT for NMR prediction. And I thought I would start by pointing to this now old review from my group where we kind of cover the history of the development of computational prediction of chemical shifts. And I don't want to dwell on the history, but I did just want to point out that this is a field that really was developed with contributions from physical chemists, specifically theoretical physical chemists, but also experimental physical chemists, physical organic chemists, computational chemists, even synthetic organic chemists. I used to be a synthetic organic chemist until I realized I was doing too much damage to synthetic organic labs, so I switched to computations. And so this is really truly an interdisciplinary field, and the same is true of the applications of the methods that have come out of this field. So if you want to know more about the history, I'll just point you to this review, and I'll just jump in and say a little bit about DFT, since that's what we're talking about today. So density functional theory is a quantum mechanical method. It's a special flavor of quantum mechanics. And I thought I would just start by contrasting that with classical mechanics or molecular mechanics or force field methods that you may be familiar with. And I'm an organic chemist, as I mentioned. And so both of these methods can be used to optimize the geometries of molecules and calculate their energies and properties. But they're fundamentally different. And without going into essentially any math, I just want to contrast these methods and point out a couple of things. So the classical mechanics or force field or molecular mechanics methods are really empirical. So they're based on parameters derived either from experiment or from quantum mechanics calculations. And those are things that allow you to get at geometries and properties, for example. Whereas quantum mechanics methods are from first principles or ab initio. You'll often hear that term. The DFT has parameters in it, but it's a different sort of parameterization that we can go into more later if you're interested. And the key difference really is that in classical mechanics calculation, so if you run a molecular mechanics calculation to calculate a structure, you're pretty much ignoring the electrons. You're really trying to solve everything based on the positions of the atomic nuclei. So if you want to get a bond distance, which of course depends on the electrons, you don't actually treat the electrons explicitly. Instead, you have parameters based on what are known preferred bond distances and so forth. And that allows your calculations to be super fast, but then you worry about accuracy. In quantum mechanics calculation, your primary focus are the electrons, and then you deal with the nuclei secondarily, in a sense. So you can do everything from the ground up. And so you don't have to worry about what's known experimentally. If your quantum mechanical method is working, it should get the right answer just based on good physics. And not all quantum mechanics methods are equal, and they have their own particular problems, but again, this is sort of a ground up calculation. And of course, this makes it more expensive, and expensive to a computational chemist is time. How long are you willing to wait, or how many computers are you willing to use to get a certain result? So there also have been, many NMR prediction methods that are just completely parameter based, don't even really pay attention to the specific geometries, just based on connectivity. Those are even faster. But again, in general, historically, but not in recent time, but historically, the faster your calculation, the less you can trust it. But we'll hear later today about some fast calculations that you can trust, and we'll see why things have changed. What I'm going to do, though, is talk about an example from my group, my favorite sort of case study, just as an illustrative example to show you how you do things, or how you can do things. And this is using one particular method that we didn't invent. And there are a lot of related approaches that will get you the same sort of results. And then I'll point out some of the outstanding problems in the field, and some of the directions people are going, to kind of set up the talks you're going to see after mine. Okay, so this approach is one where we had a reason, and I'll tell you why in a minute, for wanting to compute NMR chemical shifts and coupling constants. And so this is kind of our standard approach, and this was done by a former grad student of mine, Mike Lodovike, who's carrying in this picture a gigantic funnel. I'm a computational person, but I have the biggest funnel in my department, which is one of my claims to fame. And so we're interested, and we have been for a long time, in terpene and terpenoid natural products. So here's one, and I show you this one just to show you that the kind of methods we're using work. So this is a structure whose identity is not in question, and I'm going to show you a structure whose identity was in question. But I want to show you that the methods we're using can get known structures correct. We always have to do our control experiments. So here's the method we're using. This is typical quantum chemistry gobbledygook. The blue shorthand is the flavor of density functional theory we use to get our geometries. The red is the flavor of density functional theory we use to calculate our energies and our NMR properties. And in parentheses, you see the word scaled. So the approach that we're using here is called a linear scaling approach. So, and in this case, we're using scaling factors developed by Bally and Rablin. And so what is done in this case is the quantum calculation doesn't spit out a chemical shift. It spits out an isotropic shielding value, which is an inherent property of the molecule, whereas a chemical shift is on a relative scale. And so what is done is you take a certain set of molecules for which the chemical shifts are known experimentally, and then you compute the isotropic shielding values, and you can plot those against each other in a plot like this. And if your method is any good, you should get a straight line with not too much scatter, and that's what you see here. And then you can just take your computed isotropic shift and convert it into a chemical shift, just using the equation for a line. Okay, and your scaling factors are the slope and intercept of this line. And why would you want to do this? Well, the other approach that's standard is to use a standard, like calculate TMS, but TMS is surprisingly annoying to calculate, although you don't have to do it every time, and that works fine as well. Or you can use multiple standards. You could calculate benzene as a standard for aromatic molecules, and an alkane is a standard for other things, and so forth. So there are a variety of different approaches, and they all work for these sorts of molecules. But we like the scaling approach. And so when we do this, this is what we get. So here's a ball and stick picture of this geometry that we compute. And on each hydrogen and each carbon, there are two sets of numbers. So the hydrogens are in red and the carbons are in blue. And one set of numbers are computed numbers, and one set are experimental numbers. And honestly, I haven't looked at this slide in a while. I forget which is which, but that's okay because they all match really well. And you can see, maybe this will appear. Yeah. So in the little box here, you have the mean absolute deviation between the computed and experimental values. And for carbons, it's about 2 ppm, and for protons, it's under 0.1 ppm. And so, you know, you'd be hard pressed to do better than this. This is a pretty good agreement, I think, and this is good enough to be confident that a structure is wrong. You're never quite sure that there's not another structure that's equally good, but again, here we knew what the right structure was. We want to make sure we were getting the correct shifts. So we're pretty confident here. I'll show you just one other one. Is another terpenoid of a similar size and a similar complexity and oxidation level, and same thing. So in this case, mean absolute deviation for carbons, again, same exact method, a little under 2 ppm, and for protons, 0.1 ppm. So we're confident that if we have the right structure, we should get agreement of this level. So why am I telling you this? Well, because we were interested in this structure called aplodactone. Oh, actually, this is another one that's known. I'll show you first. So we were interested in a structure I'm going to show you in the next slide that has in it what's called a laterane unit. So that's a series of fused 4-membered rings, fused cyclobutanes. And this is the only other laterane terpenoid that was known at the time. And this one had a crystal structure, so we used this one as a test as well. And again, you can see mean absolute deviation for carbon, here 1.5, proton under 0.1. And that, I'll point out though, is if you leave out this carbon here, this carbon's connected to a bromine, and that's a well-known problem if you're connected to a heavy atom. And your definition of heavy depends on the context in which you're in. But here, if you go down the periodic table a little bit, you start to get relativistic effects. And so we just leave that out, although you can have corrections for that as well. So this is another one that works just fine. Okay, the molecule we were interested in was this other laterane called the quatolide, which was isolated and described in 1989. And we were interested in this because I wanted to know how it was biosynthesized, and we were going to start some quantum calculations to try to address its biosynthesis. And I thought, hey, wait a minute, you know, maybe I ought to make sure the structure was correct. And this is one of the first projects we did that got us into computing NMR chemical shifts and coupling constants. And you know, nowadays I tell all my synthetic organic friends or their students, hey, if your boss tells you, you know, do this total synthesis, it's going to take you 3 years. And if there's not a crystal structure of the product, maybe you should calculate the NMR first to make sure you're going after the right structure. So we do that computationally too. So when we do exactly the same approach that I've shown you, this is what you get. And let me just point out a few things. The mean absolute deviation for carbon is now over 7. For protons, it's over 0.3 ppm. You know, you could do that well without a computer, right? And here are 4 carbons that are off by more than 10 ppm. Here's a carbon that's off by more than 20. Here are 2 methyl groups on the same carbon. Experimentally, they have these. The bottom numbers here, I remember, are the experimental ones. They have essentially the same chemical shift, but computationally they have quite different chemical shifts. And here's a proton that's off by a ppm and a half. Okay, that's clearly unacceptable. Right. So we can say with, to my mind, 100% certainty at the time, this structure is wrong. But that now leaves us with the problem of what is the correct structure. And we're going to hear a lot more about how do you get the correct structure later, but we weren't fancy at the time. So how we went after the correct structure, which is what we still do sometimes, is we just dream up other structures and we calculate them and see if they're a better match. So poor Mike in my group, you know, calculated about 100 structures or so. You know, here are a few of them. We kept the parts of the molecule that we thought were reasonable based on analyzing the NMR data and thinking about biosynthesis, and none of these were good matches. And I went out and started giving talks and talking about this and inviting the audience, you know, hey, if anyone can come up with a structure we haven't thought of and it turns out to be right, you can be on our paper. And that actually worked. So I was giving a talk at Wake Forest, and Paul Jones, who's a natural products chemist there, suggested this structure. And we had looked at things that were very similar to this, but not quite this. And if you calculate this one, you get a really good match. The mean absolute deviation for protons is, again, 0.1 ppm, and for carbons, it's under 1.5. So we were pretty sure this was the correct structure. So this was great. So we thought, well, should we publish this? And then I was talking to my colleague, Jared Shaw. Here he is. He's a synthetic organic chemist. And I was kind of getting his opinion on this. And he said, well, we tried to reach out to the isolation chemists and we never heard back from them. He said, I think I can get the plant that makes this. Maybe we should try to re-isolate it and do some more involved NMR and see what we can find. I'm like, oh, that sounds cool. So let's do that. And then I learned how hard it is to get plants. So this plant is a weed that grows in Brazil. Plants, you got to pay attention to the time of year when you harvest them. So you have to wait for them to grow. And you get the plant. This is exactly, there are the Google Earth coordinates if you want to know where we got this plant. You dig up this plant, you dry it, you document it as you're supposed to, you send it into the US. Even though it looks like dried oregano, it still made it into the US. And Jared had a postdoc who was great. He re-isolated this, did some more involved NMR, everything pointed to the correct structure. And I said, oh, great, we should publish this. He said, well, I'm a little worried about some of the coupling constants. And so he was worried about this particular coupling constant here between the proton on carbon 2 and the proton on carbon 10. He's like, well, those are kind of far apart. Why do they couple so large? And I'm like, well, that's not a problem. That's a W coupling. It's like, well, I don't know if I believe it. I'm saying, but it's okay. We can calculate that. So we again use a linear scaling approach, but again, you don't have to do a scaling approach. And when we do that, we get 7, which is what's observed experimentally. So that's just right. And if you're interested, the coupling between the protons on adjacent carbons is 0 for exactly the reason you would have been taught in a class. They're essentially, those bonds have a dihedral angle of about 90. So if you ever looked at the Karplus curve, they shouldn't couple very well to each other. So this molecule makes perfect sense. I'm like, okay, let's publish it. And then Jared said, well, I don't really believe anything without a crystal structure. And I said, what's wrong with you? We have a good relationship, Jared and I. And I'm like, okay, well, you can try for a little bit to get a crystal structure. And then he got one. That was kind of frustrating. But of course, it was the right structure. So here's the paper. So Mike was my student. Christian was the postdoc. Paul was the guy who suggested the structure. So I'm true to my word. Marilyn was the crystallographer. Juan got us the plant, and Jared and I. And like, well, what am I going to do with this crystal structure? If I put this crystal structure in the paper, no one's going to read the parts about the calculations. Right? I know how organic chemists are. Oh, look at the crystal structure. That's what it is. So there it is. It's really faint. You're not supposed to see it very well. It's in the supporting information for this paper. So I won that one. It's because the point of this paper was you don't need to have a crystal structure to do this. But this is the evidence that convinced everyone that this was reasonable. This is not where the story ended. My favorite part of the story was after this, because once we release this structure. I'll say first, the structure makes sense from a biosynthetic perspective. So this was the originally proposed structure, and this is a known natural product. So the biosynthesis proposal originally was this could have come from a 2+2 photocyclo addition. And I don't know how we missed this in our searching, and this is what prompted our friend Paul to suggest this. If you just rotate this alkene from, this from an S cis to an S trans, and then do the 2+2, you get the actual correct structure of the natural product. So that makes sense. So once we release this structure, though, this is kind of a cool structure in a natural product. So people start trying to make it. So there were a couple of total syntheses, one in 2015, one in 2016, another one not long after that, no, 2019. I don't have the final reference on here. And this I thought was hilarious, because I never thought, as a computational chemist, I would do something that made total synthesis people do work, which is it's like my greatest achievement. In this synthesis, though, they also made the wrong structure on purpose, and it matched our predicted chemical shifts, which was pretty cool as well. So this is just an example of the kind of things one can do with DFT. And again, if you have the right structure, you should get a good prediction. If you don't, you have the wrong structure, and we'll return later in this to how do you get the right structure if you know you have the wrong one. Okay, I'll just point out that you can do this approach for nuclei other than carbons and hydrogens if you care. We've made scaling factors for fluorine and phosphorus that we never published, but other people have published those, where we've revised structures where that are hard to assign because in these structures are a lot of fluorines. And so this arrow is pointing to the deviation between experiment and theory. And if you move the fluorine over one, you get a much better match. So you can do that for other nuclei as well. So it was mentioned that we put all these scaling factors from us and other people on our website, Cheshire NMR. .info. Not a lot of .info sites out there, but we have one, which stands for Chemical Shift Repository. It's actually now called Cheshire CAT because coupling constants are added too. So if you want to use linear scaling, you can just go look up scaling factors for a bunch of different levels of theory. You don't have to develop your own. Okay, so what are other people doing? More modern people. There are people like Rob Payton, and we'll hear more about these kind of things later. So I just picked Rob because I know him. Who are using machine learning type approaches, neural network type approaches to essentially reproduce DFT results. And I also picked Rob because he has this handy website called Cascade. If you go to Cascade, you can draw in your structure and it'll predict your chemical shifts very quickly, and you'll get pretty close to DFT quality results. And even if we're going to do DFT calculations now, we kind of do that as a starting point to decide whether or not we want to invest in more expensive calculations. So that's one thing that's going on. Also, I'll just point you to this book chapter, which, even though it's a book, it's available online. I think you can download it. That we wrote recently, which has actual laid out practical guidelines for running these sorts of calculations. The approach I described and other ones, caveats about various things. So this is the most practical thing we've written about how to do these sorts of calculations that just came out. It says 2023, but I don't even know if it came out before 2024. So that's a resource if you're interested. So to finish, I'll just point to a few problems that I worry about and that I probably won't solve. So maybe someone else on the call will, or and tell me about it. One sounds like it should be a simple problem, but it's a horrible problem, and it's the problem of conformational analysis. So the molecules I showed you were all very rigid. Either they only had one predominant conformation or just a couple. But there are plenty of molecules that are very flexible. And if you're trying to reproduce something that happens in an NMR tube, you have an ensemble of conformations, and you need to get all those conformations, and you have to get the relative amounts of them correctly because they all have at least slightly different chemical shifts. Generating all the conformations has issues, but the harder problem is actually getting their relative free energies correct, and which is largely a problem with entropy, but not entirely. So sometimes we actually just avoid the problem, and if we think we might have a decent structure, we don't make a Boltzmann distribution and weight the conformations based on their energies. We just weight them to give the best match with experiment, which is 100% cheating. But it basically says, well, if assuming we messed up the energies, could this structure possibly match the experiment? And if not, we definitely throw it out. If yes, then we keep it in the pool of structures. On the flip side, if you know the structure is correct, you can use exactly that approach to tell you what the distribution of conformers is, which can also be handy in other contexts. And there was even just this recent paper that doesn't have page numbers yet, essentially describing this exact approach, if you're interested. Okay. Another problem that we worked on a little bit that pains me and pains my synthetic friends as well, are when you have ionizable groups like amines and carboxylic acids. You look up an experimental spectrum of an alkaloid natural product, and often there's one spectrum. But is it? Sometimes they'll say, but often they don't. Is it the free base? Is it the salt? Usually it's somewhere in between. And rarely do you see an NMR titration, and they can make a difference. So here's a case we looked at for a carboxylic acid where the alpha proton varies by almost half a ppm, depending on whether it's the carboxylic acid or the carboxylate in solution. And you might have a mixture of these. They might be interacting with each other in dimers, and that's concentration dependent. And so this is another unsolved problem that I wish someone would just solve for. And then the worst problem of all that you're going to hear a lot about as we go forward is how do you actually predict the structure from the spectrum? So again, in my context, if you know that the structure is wrong, well, what is the right structure? And I'll just say that this is the Holy Grail. This is my favorite Holy Grail image. And I won't say anything about that because we're not good at that, but we will soon hear from people who are good at that. And with that, I will leave you and hand you off to the next speaker. Thanks a lot.
Thank you, Dean. Thank you. Very good introduction and the good points that you at the end summarize the critical points for the DFT to improve in. I think we all were thinking about one way or another of all these three problems, and we will address them in maybe some of them. So our second speaker, Dr. Ryan Cohen, so please take it away.
Okay, thanks. Just one sec.
Want to mention our sponsors as always as well. MR Resources, been around for nearly 40 years at this point, and offering virtually any and every sort of repair service, maintenance service that you might need for your Brooker systems, any Brooker systems, Avance 3s, Avance 3 HDs, Neos, Ultra Shield Plus magnets, Ascend magnets, on and on and on. They're equipped to handle it, quench recovery, system relocations, repairs. They've got also a very, very well-equipped probe shop. Can do, once again, literally anything and everything with cryo probes and cryo platforms. Do check them out if you would.
Yeah, so yeah, thank you, Alexei, for the introduction, and also it's really nice to hear the Aquatolite story from Dean. I've certainly read about it, but never actually saw that presentation myself, so that was really exciting. So what do I do at Merck? So I've been at Merck for close to 20 years now. I actually started my career the first probably 10 years or so was doing LC, GC, and mass spec method development. And then I saw an opportunity with some long-term colleagues in the NMR group that retired to move over, transition into the NMR group. So I've been doing NMR for the last 10 years. So one of these guys actually was kind of a legend in the group. He worked here for almost 40 years, I think. And so when he was leaving, I was like, hey, Bob, do you have any advice, for someone new to NMR spectroscopy, and he said, yeah, sure. He said, you could solve 100 structures correct, Ryan, but you make one mistake and they always remember the one mistake that you made. And I was like, wow, that's so basically you're saying just, don't mess up, and, so I was thinking to myself, I was like, all right, I don't want to get kicked out of this group. This is my dream to become an NMR spectroscopist. So I better, make a very low number of errors. So how do I do that exactly? And so at the time, Alexei was probably the only person in the group that was really running DFT calculations, at least on a regular basis by himself. And so I was like, well, I had some experience when I was an undergrad, actually. I did an RU doing some DFT benchmarking. So I was like, well, let me try to learn that. And so I did, and I guess my actual error rate is quite a bit less than 1%. I've solved actually probably thousands of structures in the last decade or so, and these are some of the areas that some of the questions that I see and areas where I apply DFT regularly. So it's not just actually NMR. It's also doing absolute configuration analysis using ECD and vibrational circular dichroism. spectroscopy. We do some radical studies using EPR spectroscopy. So pretty much use it for, you could say these are the 8 big areas. So I use it for pretty much everything except for just doing regulatory filings, assigning spectra for that, and also QNMR assays. So I'm a huge believer in it. So when I first got started too, there wasn't really, a lot of it was manual basically. And so I was like, it was way too time consuming. I was actually getting bombarded with too many problems at once, and trying to do DFT for everything was incredible, to try to do that. So I was like, I better learn Python. And so I wound up teaching myself Python and Linux shell scripting. And I kind of wrote a whole bunch of different scripts to sort of automate the process. So and then we wound up, I used it myself, but I also told other people in the scripts. There's actually about 20 spectroscopists at Merck, roughly, give or take, located at different sites. And a lot of them are using these scripts, fortunately. So, basically the way our workflow goes is that the first part is a conformer generation step. And we use multiple conformer generators, which tries to give us a very robust and full ensemble. So we're trying not to miss conformers. And then we also remove, any redundancies. And we do some clustering. And then the next step is we do our DFT calculations predominantly using Gaussian 16. Then there's automatic processing, and we can visualize in PyMol. And then final results are done in Excel, by comparing, instead of mean absolute deviations like Dean was saying, we're actually using RMSD, but you could also do DP4 type, analyses. So, depending on what your flavor is. So, but we kind of, go with RMSD errors. So when I was developing those scripts, the question was really, what is the best model chemistry to use? And so Dean touched on that. With the Cheshire website, that was, a lot of people in our group, would go to that, and I had initially started with that as well, but I was like, well, can I do better? Plus there's a lot of benchmark papers that have been done. This is probably just a subset of all the chemical shift benchmarking studies. So one paper in particular that kind of like inspired this work was, it was done by Mark Irons in 2017. And Mark also looked at was using Gaussian 16. And so it was kind of like testing a lot of functionals and a lot of basis sets in there. And so I was looking at the results of that, and I was kind of surprised because he was saying, and this was actually just for really carbon chemical shift predictions. And I was surprised because, he was saying, oh, instead of using GIAO, for your, NMR prediction method, he was using the continuous set of gauge transformation, so CSGT, which is, less common. And then also using a range corrected functional LC hyphen TPSS. So I was kind of surprised by both of those things. So, and I'll come back to that, but this was just saying, okay, what really is the best method? So the first part was kind of like, okay, if I want to do my own benchmark study, I need to come up with a training set. And so inspired by the Cheshire website, I looked at the molecules that they had already evaluated, and evaluate and getting some of those scaling factors. So, but I was like, let me remove a couple of these guys, just because let's not deal with compounds that have heavy atom effects, because, of the relativistic problem that Dean mentioned. Also molecules that have multiple conformers, that's an issue. So let's only deal with molecules that have predominantly, like more than 90% one conformer, as well as compounds with exchangeable protons. So let's remove that. And then we wound up getting 50 compounds. Actually, it's the ones that are in black, but not all of them. So for instance, we didn't use, molecules like the cyclopropyl dimer, where we couldn't actually obtain it. So what we wanted to do additionally was to remeasure the chemical shift. So I'm mostly an experimentalist, and we're just doing computational chemistry to, reinforce those experimental results. So we wanted to remeasure these things. And then one of the drivers was a lot of those chemical shifts were kind of old, right? Where the spectrometers used at the time, were not as sensitive as the cryoprobes that we have these days and the higher field magnets. So We were worried about if there was aggregation issues for one. Also, these were done in chloroform, and so because chloroform has some residual DCl in there, we were worried about partial protonation of some of the nitrogen-containing species. So you could see, for instance, A and B just so for pyridazine. You could show with neutralizing the DCl with potassium carbonate, you know, and without. So, so we want to, and we also to avoid the aggregation effects, we want to measure everything at 1 millimolar. And so, you know, this just shows some compounds, some of the aromatic ones that happen to deviate a bit, you know, when you're at higher concentration. And so we compared the deviations, you know, that were previously for chemical shifts previously reported and the ones that we measured. And for the most part, they're pretty close, but there was definitely some outliers. So that was giving a more robust test set for our benchmark. And then the way that we did the benchmarking was we first evaluated all the functionals that were available in Gaussian 16, which was about 73 of them. We then went on to look at a whole bunch of different basis sets, the 3 different gauge referencing schemes, geometry optimization, and then the implicit solvent, you know, used for the NMR chemical shift piece. And the order of evaluation that we did was such that we thought that the density functionals would make the biggest difference, and then kind of going down to like what lower differences would imply. So, so this generated a whole bunch of, you know, kind of eye charts. And so I only show one. The rest you could look up in the paper. It's available open access online. But essentially what we found was the best proton functional was WPO4, which wasn't surprising. That was actually reported in the Cheshire website that as probably the best performing one, because it was actually designed for proton chemical shift prediction. Surprisingly, WCO4, which was designed for carbon chemical shift prediction in the same paper by Kramer, actually doesn't perform very well for carbon chemical shift prediction, which there's reasons behind that. But anyways, the best one for carbon chemical shift prediction was Omega B97 XD, which, you know, again, other people have found that too, but what we want to reaffirm that. So, so this was good. And TPSS didn't perform very well, LCTPSS. So, actually, you can see the maximum deviation here. It's hard to see, but it's 7. It's above 7. So, and we were getting less than 4 or around 4 for, you know, for Omega B97 XD. And so here you can see just some of the residuals from those linear scaling plots. So Hartree-Fock, you're getting, you know, deviations up to 10 ppm. SVWN is a tier 1 or LDA type functional. And is also giving pretty bad deviations. And then you go to GGA is a little bit better. And then once you get to the hybrids, like B3-ELIP actually performs really well. And then Omega B97 XD, you can see performs really good. LCTPSS, like I mentioned, actually didn't perform very well. So I'm not totally sure what happened, you know, how irons got that result, but you know, suffice it to say, we also tested GIAO against CSGT and the other gauge referencing scheme, and we found that it's superior, particularly at lower, smaller basis sets. The basis sets give smaller basis sets generally actually paradoxically work better for carbon. When you get to higher basis sets, the kind of accuracy sort of goes down. The opposite is true for proton. So a lot of times you wind up dividing what linear scaling factors and what method you would use for proton versus carbon, but you would try to use the same geometry optimization because the actual chemical shift prediction itself is actually pretty quick. We also found that implicit solvent, you know, does improve results over using gas phase calculation, but different implicit solvent methods are pretty similar. And then I think probably the most surprising thing I guess we found was for the geometry optimization step. It could be quite important, particularly going up to triple zeta basis sets. You can get more accurate carbon chemical shift predictions. So these sort of show the 2 methods and the scaling factors that we recommended from this paper. So basically the high accuracy one is pretty much what everyone in the group at Merck is really using and finding really good results. And so then we wanted to test it versus our own probe molecules. So this time we weren't restricting ourselves to just rigid molecules. We looked at, some, compounds that have quite a number of conformers like Taxol, and some of these strychnine, sort of dimers and stuff like that in there. This just shows also that, we wanted to also see if there was a, some, with our methods, some areas, some functional groups don't perform particularly well. So we do see that olefins, sometimes can be problematic and difficult to get that electron density right. So that would be possible further improvement, and, in designing new functionals, can go after some of those. So we do see that the areas where carbon deviates a lot is close to proton, but not exactly the same atom, which was like a little bit surprising from this plot. So, and then this table basically just shows like how we compared the two methods, method 1 and method 2 versus previous DFT studies. So generally method 2 outperforms method 1. We're getting lower RMSD errors, lower maximum deviations, and we're generally outperforming other things in the literature. Some of these studies, I should point out, were actually designed to find the best functional that worked for that particular molecule, whereas ours is kind of more of a general method. So the worst errors that we're getting max for method 2, at least the more time consuming one, we're getting maximum deviations up to about 6 ppm, for instance, for paclitaxel and some of those strychnine molecules, but generally, pretty low, less than 5 ppm. So this kind of gives us a cutoff to say, if we have unknowns, for instance, that we're proposing, if we can, believe that structure is likely correct. But we also use other data too, coupling constants and, two-dimensional NMR correlations like, most spectroscopists would use. So that's pretty much it. I probably went over a little over time, but yeah. So, all right. Well, thank you for that.
Okay, thank you, Ryan. This is exciting. Yes, as I was expecting. That's the work that Ryan is doing is so thorough, so comprehensive. So this is a nice sort of overview that, anyways, it's showing that the J NMR sort of setting where there are like 200 different settings is actually in a very good place. It can still be improved a little bit, and maybe you will sort of, Dean, maybe you'll consider to include the Ryan's functionals in your table as well.
Good afternoon. Q1 is dedicated to developing NMR hardware and software to make routine NMR more accessible to a broad range of scientists and engineers. The company aims to establish new and innovative products for demanding applications across sciences. Our products consist of complete systems at 400 megahertz with magnets manufactured by Q1. We also offer complete systems with magnets from MR resources up to 600 megahertz. Our console upgrades in 2 or 3 channels from 300 to 600 megahertz, with the economy console consisting of the Quantum 1 Plus console, preamplifier, workstation, and utilizes the existing magnet probe and shims. This is by far the most economical upgrade in the market. A full upgrade consists of the Quantum 1 Plus console, preamplifier, broadband STM gradient probe, and sample changer for a completely automated system at a price that would surprise you. And our smart tune and match probes for Brooker invariant systems for improved throughput and reliability. Q1 probes are fully integrated into the Topspin and vNMR-J platforms. The Q-Link Ethernet-based interface can be installed on a wide range of consoles to fully automate the operation of older NMR systems and add multi-nuclear capability to your dual or quad nucleus spectrometer. Want to know more about our probes, consoles, and complete systems? Contact us for more information or a remote demonstration. Thank you.
So let's move on. So we have almost on schedule. Let me share my screen again. So this is my portion of this talks that we prepared. So I'm going to talk about the combination of the DFT with the computer-assisted structure elucidation and how it can be used in structure elucidation, verification, and revisions. And I just want to start with this overall definition. What is if somebody doesn't know what case means, but that thing has been around for at least 50 years and has been developed continuously. and now it is sort of in the stage that it's very reliable. So the computer-assisted structure elucidation is they call it the expert systems. That is one of the points that the dean made in his presentations, how to derive the structure from the spectra, and that's this expert system does. So it's deriving the structure from the molecular formula, which is usually we're getting from the mass spec, and then you feed to the program NMR data, the chemical shifts, proton carbon chemical shifts, and the 2D correlations. Those are listed here: COSH, SQCH, MBC. And from that point on, the program takes over and creates the molecular diagram, which is based on the correlations that it assumes for different experiments, and then start generating very quickly all possible substructures that will combine in the full structure. And while it does that, it calculates the chemical shifts. And what it does it very quickly because you're generating a lot of fragments. The speed of the calculation of the chemical shifts is a bottleneck here, and the developers of that programs have been approached that with very quick empirical predictions, and so they could calculate 30,000 chemical shifts per second. So when you generate 1 million of the structures, so you can then after that you can rank those structures very quickly. Of course, the accuracy of the chemical shifts of the empirically predicted is not very high. That's why in the process of the generation of the structures, they're using very rude algorithm, and at the end, they will do the ranking with either with a host code-based analysis, which is much slower, or artificial neural network chemical shift analysis. But nevertheless, this is empirically based chemical shift data. So as successful that program has been so far, there are still the limitations of the case. And as you understand, the limitations comes from the assumptions that the program is using. First of all, the empirical chemical shift predictions might not be sufficiently accurate in order to do the final differentiation of the structures. Because if the fragment is not present in the database that this is the prediction is based on, then that fragment would be very difficult to predict. There is no analysis of the stereochemistry, so only constitutional isomers is at the end of that analysis. That's a big thing anyway, but it's many researchers, and us including, of course, we're interested in the stereochemical analysis. And that's another limitation. The third limitation is that when the program constructs the MCD, molecular connectivity diagram, it's using the certain assumptions about HMBC experiments. That is the assumption number one, that it's only 2 and 3 bond correlations should be considered as viable. And quite often after that, the program would not be converged. So what they're doing after that, they allowed to assign the certain correlations to a larger number of bonds between the atoms. And that creates the uncertainty, because that is then done ad hoc just to converge, and the program doesn't do verification of all of that. So all these 3 limitations actually could be addressed by the DFT. And that's what we have done. So we're taking the case that is just described by Dean, the equator and the all difficulties that the team at the UC Davis went through just to get the right structure and to convince the people around. So if you will take that originally published data, you don't make any additional experiments, just the published data for the equator light, and you put that into the case program, and it's after 50 milliseconds, it will spit out the 3 plausible structures, which will be ranked like number 1, number 2, number 3. Only 50 milliseconds. And it will give you only these structures which would be satisfying the correlations and the chemical shift that the program is finding. But as you may see, the predictions of the errors of the carbon chemicals is very high. So it is because this is a very strange scaffold, and the program has a difficulty to predict those chemical shifts. So we've taken the DFT, and of course, after just calculating the most highly ranked structures from the whole list of the possible structures, we can prove it by DFT that now structure number 1 is exactly the structure that we're looking for. And as the errors that you see here is pretty good for the carbon, and the carbon chemical shift, I have to say, this is the major factor that the program is based on. So this is so think about that, how more efficient, how accurately the program works in this case if you combine it with the DFT. The other problem that I mentioned is the stereochemical analysis. So the Homital has been revised, and the case has been used for the revision, and the scaffold have been proven by the empirical chemical shifts that doesn't need to be even analyzed by DFT. That it was clear. But at the end, that molecule has 5 chiral centers. 5 chiral centers, 32 possible stereoisomers, and 16 pairs of enantiomers. So we calculate all of that using the DFT. The confirmation analysis has been done using the molecular mechanics, but then the structures were re-optimized with the DFT. And again, now ranking the structures based on the RMSD of the chemical shift, both proton and carbon, we could assign the right isomers, and that would be taken out. We could differentiate this the right isomer from that pool of the 32 different isomers. The accuracy of DFT is that's the critical here, which has allowed us to do that work. The third point that I mentioned before is that that's uncertainties about the generation when the molecule starts assuming the number of bonds between the atoms in order to generate, and that just came up as an example in a Cleos-Pinol's analysis and revision of the structure. So after the analysis, the case predicted that there are 6 structures which have a very similar RMSD, but and it was difficult to differentiate them based on RMSD only. So, but each of the structures would have a different number of those non-standard correlations. Non-standard correlations mean that they're longer than 3 and 4 bonds. So in that case, of course, we can use the DFT to calculate the J-couplings, because we know that the cross peaks in the HMBC, they are related to the value of the J-coupling. We found on a test set of the compounds, they found that usually the people observe HMBC spectra in an average, so to speak, NMR spectrometer over the last 20 years. So the coupling constant that would generate the cross peak in a published data is actually should be higher than 0.3 hertz. That's again, it's empirical finding. So we use that as a rule to look for those non-standard correlations for these 6 candidates and rank now them based on the violations of that rule. As you can see, the structure number 1, which is consistent with the revised structure, has the lowest number of these violations. Again, this is like orthogonal methods to differentiate the structures using now instead of J-couplings, instead of the chemical shifts, is using J-couplings. And my last example of the case in DFT study, again, it came in the first introduction. So the chemists very like to do total synthesis, and they're probably very proud of doing that. And so the total synthesis, as you understand, is a very time and resource consuming. So you can spend years. Some of the structures has been revised, and it took like 10 years to revise it, because they would come and go. They know that the structure is wrong, because when they start synthesizing the structure that has been proposed, this is 12 structures proposed in the left columns, and then they found, oh, we synthesized, but the result is different. And then they know that this is something wrong. So, and then they would guess what's to do, and then it takes time, again, resources, and then eventually they would do the right thing, that they would produce the right structures with the total synthesis. So we show that as Dean said, before you start going into the synthesis of the structure that has been published, go and check whether there is any violations of the chemical shifts. And if you do case, you just do the empirical analysis of the chemical shift, you see that the biggest violations could be found on almost all of these structures. So that would be a warning sign that the structure is wrong. And what to do next? So of course you can go with the total synthesis, but what we suggested to do the case, and that is the time now that it took for us to get the right structure by the case. So it's all of them is below 6 minutes. So that's the time. And actually I have to say, we used in all of this data, we have the originally published NMR data. And in some cases, particularly on those where there are minutes, the data were not complete. So the case could recognize the gaps. And based on that, to solve that, it will take a little bit longer time. Some of the structures have to be proved by DFT as well. It takes It takes a little bit longer time, maybe a day or two, but it's not years. And that is the way how we kind of now advertising that approach among the chemists. And and as I said, it's this is our general suggested protocol for the people who are trying to do that kind of work. So go first, as Dean suggested, to do the chemical shift evaluation, verification, then after that, do the case, and if needed, to do the DFT. So this is my short presentation about the synergy between the two methods. And I have to say, so the cases would definitely benefit from adding the DFT part into that, because it does configuration analysis, conformational flexible molecules. We can do that as well. There is no time for that to spend, but that's definitely the power of the method, the high accuracy of the prediction chemical shifts, for sure, and also the capability of calculating of the J-couplings. It also makes the high confidence in the results that we are getting from this case analysis as well. But I also want to say that the benefits of the case using for the DFT, because the DFT is usually used as a method of verification. And as we pointed out before, so it is not necessarily that it's only one structure could be as consistent with your NMR data. So combining the case with the DFT would sort of prove the DFT method as a structure elucidation method. So this is my last slide. I want to acknowledge also the people who have been involved in that, my Merck colleagues, and as well as the people from the ACD labs, which is doing the case. But they are not the only one who is working on the case type of expert system. There are multiple others, but that is my colleagues. And thank you for your attention. And I will stop here, and we'll give the opportunity to finish our webinar to Craig Botts. Please go ahead, Craig.
Thanks a lot, Alexei. And now I'm going to start off by just saying that Dean, Alexei, and Ryan and I did not coordinate what you're going to see over the next 15 minutes or so. Dean, in fact, can confirm that I sent him a Zoom message a few minutes ago asking for some information that hopefully, if Zoom plays nicely, I can show you the outcome from in a few minutes. But that's set up really, really nicely, because pretty much you can take everything that's been talked about over the last sort of 45, 50 minutes or so, take the words DFT, and hopefully I'm going to convince you that you can replace them with the words machine learning, and take anything that involved hours and days and turn it into milliseconds or seconds. That's the goal. I'll see how close I get. Lovely. So it's a different title for the same thing. Basically, can we teach machine learning to do NMR better than quantum mechanics? The simple answer is we can do it just as accurately, but hopefully much, much quicker. That's the goal. And this is my team of miscreants, past and present, who've been working towards this for a few years now. So if I just click that through, there we go. So in the top corner there's Will, who did start off this whole project. In his PhD interview, actually, he was aiming to do pretty much what Ryan and Dean and Alexei had talked about in terms of predicting NMR spectra from DFT. But at the time, we were worried about the fact that DFT was too slow. And in his PhD interview, he said, well, why don't you use machine learning? And I said, because I don't know how to do machine learning. And he said, well, can I give it a go? And so he did. He set up an entire machine learning program for my research group on the basis of a suggestion in his interview for his PhD in the first place. And so his idea was simply to take DFT calculations and use DFT predicted values as input data, training data for a machine learning system. So you take the data, and I'll tell you more about it in a second, but you take the data for a few hundred molecules, you teach a machine to reproduce that data, and then you take that machine and apply it to molecules it's never seen before and see how accurately it can reproduce chemical shifts, couplings, IR, spectra, whatever it is that you might want. And the way it works, so our machine is called Impression. Dean mentioned an absolutely beautiful machine neural network system of Rob Patton's that was published a couple of years ago. That came after what I'm going to describe to you now, and then before what I'm going to describe to you at the end of the talk. And so Impression is, well, there's the acronym because it's kept NMR, we have to have one. It was an hour and a half of a research group meeting to come up with that acronym. And it's basically a machine learning system to predict NMR parameters it's trained on, depending on the generation, tens of thousands to millions of DFT calculated NMR parameters. So that's 1,000 up to about 25,000 molecules. And so, yeah, the first reference, that's to Rob Patton's work, and the second one is actually to Lyndon Emsley's group, who managed to beat us to the draw on this in 2018 and published a kernel ridge regression model, which is what our original impression version was, but for solid state NMR prediction, not for solution state NMR prediction. Basically the same kind of approach, the data is different effectively. And so when you set about doing this, the fundamental problem you've got is that a computer cannot read a picture of a molecule. So you can give it a smile string, or you can give it some representation of the molecule, but it has to be readable by a computer. And so the first thing you need to do is convert a molecular structure into some kind of matrix of numbers, okay? Once you can do that, and I'm not going to go into the detail of how you do that, but you can think of that molecular representation as being X, Y, Z coordinates, that they are a molecular representation of a molecule. They're not a good one, because if you rotate a molecule, its X, Y, Z coordinates change, but the molecule hasn't. So that's what's called a rotationally variant representation. But if you take the distances between all the atoms in a molecule, you turn it, you twist it, you move it up and down, the distances don't change between the atoms. And so that's an invariant representation. And so just think of this as a matrix of distances between nuclei. That's a nice simple way to think about it. And so you take a data set of as many molecules as you can get DFT calculations for, and you put those representations into a matrix. In our first generation machine, put it into a kernel matrix, and then you give it the DFT calculated value. So you have to run the DFT predictions exactly as we've been hearing before, using whatever DFT method you like. So Ryan has an entire book full of them. We picked one, and I'll tell you what that was in just a second, but it doesn't actually matter what it is that you pick. And you take those two matrices of the structures and the target chemical shifts, and you just have to find the matrix that you can multiply K by to generate Y. And so in the inimitable words of Will in a group meeting, machine learning is just calculating alpha. That's pretty much all it is. It's finding the transformation matrix that turns K into Y. And so our first generation, as I said, was based on kernel ridge regression. It used an FCHL molecular representation, if you really care. The L comes from von Lilienfeld, who designed it, and the other three letters are from the other three authors of that paper. But it's a three-dimensional representation, so it includes distances between atoms and angles between atoms, and then those angles give you the three-dimensionality, and therefore this is a conformationally and stereochemically aware representation of molecules. We trained it using DFT structures, DFT geometries, and DFT predicted NMR parameters, and we used omega B 97 XD 631G DP, and we used that simply because it was fast enough and accurate enough that it gave us reasonable results. We understood it. We could take our entire training set and redo it with a different DFT data set or DFT method, and we would get a different machine that predicted slightly different values. But ultimately, we were after one that just reproduced this DFT method. That's our goal here. We took 882 structures from the Cambridge Structural Database. Now, that is actually 1,000 structures, and 118 of them failed in DFT. And so we just threw those away and didn't bother doing anything more with them. We didn't worry too much. But that's about 20,000 proton, 20,000 carbon chemical shifts. Just for clarity, and this is important, carbon, hydrogen, nitrogen, oxygen, fluorine only, no charged species, and fully valent. Okay, so doesn't, whoops, my screen's just gone blank. Hopefully that didn't happen to you. That means it won't deal with charged molecules. It won't deal with things with phosphorus and boron and silicon and things like that in them yet. And we tested it against 400 structures, and those structures we stole from the Emsley paper. We just took the molecules they used in their testing set and used that as ours as well. And long story short, this is what the results look like. So machine learning prediction across the bottom and DFT prediction across the on the vertical, and we get a straight line, and there's a bit of spread. Now this is a lot of numbers. This is 20,000 numbers. So actually they're very much along the diagonal line with a bit of spread to the outside, and we'll see more of that in a minute. But the fact is that these are really, really accurate. I don't know why. Why do I have the... I don't know why I have your Cheshire reference on there. I think that's meant to be on the next slide, Dean. That just shows I was editing these earlier today. Oh, that's why. And so the accuracy numbers, this is the mean absolute error, is on the order of, for this original impression, 0.3 ppm for proton and 3 ppm for carbon. And that's something that we see all the time. Proton chemical shift predictions and carbon chemical shift predictions, roughly speaking, are different by a factor of 10 because protons come on a chemical shift scale that's about 10 times bigger than 10 times smaller than carbon. And so that makes sense. Just for reference, the DFT method we were using reproduced Cheshire molecules with accuracies of around about the same order. And so our impression machine was as good at predicting DFT and then ultimately experiment as DFT was at predicting experiment. That shouldn't say CF experiment there. That impression should be against DFT. Sorry, I've misquoted that. I'll show you the experimental data in a moment from impression. But there's a problem with what I've been describing. A matrix of internuclear distances for 1,000 molecules is whatever size it is. If you double the number of molecules, the matrix gets bigger. And it doesn't get twice as big because you've added twice as many atoms and the internuclear distances, it gets 4 times bigger. You make the data set 10 times bigger, so 10,000 molecules, the matrix gets 100 times bigger. And basically after about 1,000 molecules, we blew up the RAM on our computer. And so this kernel ridge regression doesn't really scale very well, which is why we stopped that. But there's a really simple solution, and this is the one that Rob Patton came to as well, that you simply move to an architecture that doesn't require that complex representation, or at least that doesn't scale with the molecular representation, and that's a neural network. A neural network is just this thing in the bottom corner. It's a bunch of nodes that are connected to each other, and if you feed into it, you put into the input layer, so the arrow's going in on the left there, 1,000 molecules, the network doesn't change size if you then give it 10,000 molecules. It's just the same size of network. You'd have to batch the molecules up into groups of 1,000 if your computer can only handle 1,000 molecules at a time, but that's not too much of a problem. It's a linear scaling problem as well. So neural networks are a nice scaled independent method, or at least scale sufficient method of doing these calculations. And in the top corner up here, we've got Kelvin, who implemented the neural network version. Will started off, and then Kelvin continued with it. And I'll tell you about Ben and Christoph in a minute. And this is the input to that neural network. Rather than this FCHL molecular representation, we use a graph. And a graph just looks like this. You've got methane, it's got 5 atoms. Those 5 atoms are 5 blue dots, and the lines between them are the connections between them. You can call those connections bonds, you can call those connections distances, you can call those connections coupling constants. And that's kind of cool, because then it can predict the distances, the coupling constants, whatever interactions there are between any 2 atoms or 2 nodes, and the structure of the networks on the left. But the key here is that it's a transformer-based neural network that we use, and a transformer network allows you to, or it uses a technique called attention, which means that the chemical shifts for carbon and proton can then link to the coupling constants between carbon and proton, or the fluorine chemical shifts, or the nitrogen chemical shifts. So as it learns about carbon chemical shift, it uses that information to learn about proton-proton coupling constants, if there's any information there to be had. And this is the same technology that's used in ChatGPT and Llama and all of those big, large language models at the moment. So this was the cutting edge at the time that we were setting this up, and it's served us very, very well. So just to show you what we're currently at, in fact, that number's wrong. It should be 25,000 molecules are up to now that come from Cambridge Structural Database, Kimball, Otava. These are drug-like molecule databases, natural product databases. It's about 250,000 proton chemical shifts, 250,000 carbon chemical shifts, on the order of about 5 million coupling constants, proton, 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 carbon, whatever it is that DFT calculates, which is everything. The molecules that it's trained on now include sulfur and chlorine and bromine. As Dean said, you don't want to believe DFT when it comes to bromine, but we don't care. We just want to reproduce DFT with all of its benefits and its errors. And then we can correct our predictions just like you would predict DFT if you wish to. We tested it on the same 400 molecules of our first generation, and this is just for comparability, and you can see that the results are fantastic. We're now below 0.1 ppm compared to DFT. We're below 1 ppm for carbon compared to DFT. In fact, we get better results than this if we use internal holdout comparisons, but we try to make this as general as possible. And so actually, we tested it on a bunch of molecules that had never seen before. And these are a wider range of structures that include many more elements. They're the same ones that we've trained it on. But actually, these came from DFT 8K. That was Rob Patton's database of DFT molecules. We recalculated them using omega B97 because we want to do a fair comparison. But you can see that the errors don't really go up that much. They go up very slightly. And that told us that we've got a really, really generalizable machine now. Our originally published Gen 1, I'll openly admit now, was very good on small molecules that had carbon, hydrogen, nitrogen, oxygen, and fluorine most of the time. This one's very good on pretty much anything. In fact, I demonstrated it this morning. We demonstrated it this morning live on something that had sulfur in it. And they picked up on, oh, show us the carbon next to sulfur. And I was terrified because sulfur has been a bugbear for years. And it's absolutely beautiful now. It's working fantastically well. And again, just to compare, we're now well below how good DFT is compared to experiment. Okay? And again, you'll see that come back in a minute. The key here is that each and every one of the machine learning predictions that I've been talking about. So if you feed this a molecule, it will do the machine learning or impression prediction of that in milliseconds. So where DFT for a single molecule might take, depending on the method you use, minutes, hours, days, if you want to use one of the nasty ones, this can do it's down to about 10 milliseconds per molecule now. So we can do about 100 per second. And that means that we can literally run thousands or millions of molecules in a day if we want to push this. And that's on a laptop without even parallelizing it. Problem number 2. So this is one that quite rightly gets picked up. We're doing predictions on a 3D structure, and now NMR predictions take 10 milliseconds, but the 3D structures don't. You have to generate a 3D structure. And so in order to get around that problem, rather than using DFT 3D structures, we just throw at it 3D structures generated using Grimmer's GFN XTB method, which is like where Dean was talking about molecular mechanics methods. This is a semi-empirical machine learned force field kind of method thing from Stefan Grimmer. And it's really, really fast, but it gives you geometries that are almost as good as DFT. And just to prove that, taking our machine learning system trained on DFT structures and then testing it on GFN XTB structures. So it never knew that it was dealing with anything different than what it had been trained on. And the results went up marginally in error, but they're still absolutely outstanding. And if we retrained our machine using XTB structures, actually the results didn't get any better. Effectively, it hadn't learned anything about the structures where the difference between XTB and DFT methods made any difference to impression whatsoever. So we're really, really pleased about that. That's a fantastic result. And so what that means is that we can give it a molecule and it'll give us a prediction on it in seconds, if that. I think at that stage, what I'm going to do here is just stop sharing, and I'm now going to put my life in the hands of Zoom and see if I can share what I hope is that one. So hopefully you can see a screen that says Impression Gen 2 test. Is that right?
Yes, we can see it.
Beautiful. Okay, so this was a recording that was made by Calvin, my postdoc. On request from me, when I sent him a message saying, can you please run a prediction on this smile string that Dean sent to me about 15 or 20 minutes ago via Zoom. So here we go. Hopefully you'll be able to watch this happen. So he's got the smile string, he goes down, he pushes run, and there's the predictions. And those are DFT quality NMR predictions, 3D structure. You can pick your carbon, you can look at that. You can also, I think he's going to show you the 3D molecule. That's what he normally does next. Clicks on the show 3D. It's generated the 3D structure using XTB. It's got the protons, it's got the carbons, and you'll see on the left-hand side, he did proton and carbon chemical shift, HCS and CCS. He could have done 1 bond couplings, 3 bond couplings, 2 bond couplings, all at the same time. It would have taken no longer to do any of those. So that's as close to live as I can give you because I don't have a version on my laptop yet, but I will get that in the next few days. Right, if I can just get back to my PowerPoint show. Cool. There we go. Okay, great. So literally, that is how long it takes. Here's just the numbers. So 20,000 geometries. This was done by Richard and Ben over the last few weeks. They were testing these molecules for particular purposes. 20,000 geometries. So that's 8 different diastereomers of this molecule, 2,500 conforms each, just because we could. And it took Richard 2 days on his laptop, each one taking just a few seconds. And literally 99.5% of the time was the GFN XTB. It's the 3D structure calculations that take the time. It's absolutely fabulous. One problem with machine learning, just like Alexei was saying about using any kind of predictor that hasn't seen a fragment or hasn't seen a particular kind of substructure before, machine learning is just the same. If it hasn't seen a dog, it can't recognize dogs. If it hasn't seen a carbonyl, it can't recognize carbonyls. And so if we really zoom into our latest plots on prediction versus, or DFT versus machine learning, you can see there are outliers here. And I've emphasized them here. There's 250,000 data points on here, so there's not that many outliers. But those outliers are there, and some of them are huge, like 70 ppm wrong. It just gives you nonsense numbers if it doesn't know anything about the group. And so there they are, just to highlight them. And so just to give you some examples, this one here is 63 on the left is 63.3 ppm wrong. It's an alene, the central carbon of an alene, and it thought, this was the generation 1, this is a long time ago, it thought it was an alkene, it treated it like an alkene. A proton sitting above a benzene ring, what an undergraduate mistake to make. It didn't know about benzene's through space pi effects, or the ring current effects. Yeah, there's lots of examples in here where it just sees a 3D structure and it doesn't understand the chemical environment of that group well enough, and it makes a big mistake. And so the solution to that problem is basically trying to work out, come up with a way of visualizing which atoms are badly predicted. And this is a plot of, I'm going to have to bring up the next thing, error across the bottom and variance or confidence up the side. And the top is low confidence, the bottom's high confidence. And this was these confidence metrics, and I can bore you senseless with it if you like, it's a cross-validation method, but it was about seeing if we could get the machine to tell us how confident it was, and we found we could. So the left-hand side is where there's a low error, so the data is towards the left of the plot, and a medium level of confidence, so it's halfway up. The bottom is moderate errors, so this is a log scale, so that's kind of 1 ppm errors in carbon, but it's highly confident about that environment, so it's probably pretty reliably 1 ppm in or out of the right answer. But the top right-hand corner is where we really care, and that's where there's a high error in molecules and the machine has low confidence. And the color coding in this plot is key, it's functional groups. So if we just take that away, the yellow things and the orangey things are allenes and thiocarbonyls, I think they are. And so what Kelvin did was tabulated all of the different functional groups in our data set and then looked at this confidence value and could find the worst predicted things. And they're all pretty obviously groups that aren't that common. So allenes, thiocarbonyls, isothiocyanate, all sorts of weird and wonderful things like that had really high variances and very high errors. And so the solution to fix this is just you have to feed the training set a few molecules. So only 50 or 100 molecules that have allenes in them, and then it learns about allenes. And when you do that, you get this. So that was what we saw a minute ago, and this is what happens when you've added, I think it was about 80 molecules with allenes in them to the data set. Once it knows what to do with allenes, the problems go away. And so that's just something we're working on now, is just supplementing this to get rid of the egregious errors. But as I said, they're down in the 0.1% of the entire data set is that badly predicted. So I've talked about chemical shift a lot. We can do nitrogen, we can do fluorine. I was really pleased to actually see that fluorine stuff from Dean with errors of 7 ppm from DFT, and that's what we get as well. So I was a bit nervous about having 7 ppm errors on fluorine. So I'm very, very pleased that we're just as bad or just as good as DFT. But it does coupling constants, and it does all of this at the same time, simultaneously, one shot gives you all of these things. And if I'm going to sales pitch it, that's about the only difference between what we do and what Rob Patton did with his work. He can do each chemical shift and each coupling type separately. We do it all in one shot. The accuracy is give or take the same sort of thing. And the cool bit here is then you get things like, where are they? Bottom left-hand corner, 3-bond CH coupling constants, exactly what Alexei was talking about in structure elucidation. If you want to know, is there going to be an HMBC correlation, you don't want to know how many bonds there are between the atoms. You want to know what's the coupling constant. And this can give you that coupling constant on the fly. So it can check, is that absent peak or that present peak in the HMBC correct? And it's not just there's an HMBC peak here, does it have a big coupling constant? But think about it in terms of absences. There's not an HMBC peak for that proton and that carbon. Why not? And it checks that against the coupling constant on the fly. That would be so, so cool. I said I'd get to experiment. Here it is. So the blue plot is impression versus DFT. So it's really accurate. And the green and the red are impression versus experiment and DFT versus experiment. And they're pretty much the same. They give the same rough error distributions. The way I like to think about impression now is it's a drop-in for DFT. It does the same thing as DFT. And if you get results from impression, I would challenge you to tell the difference between impression and any other DFT method. Pick your flavor of DFT and it'll give you results that look just as good or just as bad as that. It doesn't mean it matches omega B97 or it matches MPW. It just looks like a different method with a different functional or a different basis set when you compare it to experiment. So that's a really, really nice place. And we're now working on how we can up that game and make it correct the data towards experiment. And I've got some thoughts there as well. So it does the diastereomer discrimination. So Alexei gave a couple of examples of DFT getting stereochemistry right. So this is it getting strychnine. It has to be strychnine if we're going to do it. And it correctly identifies the right diastereomer of strychnine from proton chemical shift. Blepharic is another one that Emiliano here in the top corner did. And DFT said that the RRRR diastereomer was the right one, and so does impression. And this was an earlier version of impression, so it should do this quite a bit better now, and certainly much, much faster. And so that kind of brings me back to this last point. And that was, I mentioned this thing about you take the internuclear distances for your training environments of your molecules, so you define the interatomic distances. Oops, I've got my decimal places in the wrong place here. I was typing this while Alexei was talking, so I put the dots in the wrong place. That should be 1.34 and 1.54 and 1.51 angstroms. But you take the internuclear distances between the atoms in a molecule, and you use that as your input, and then you try to predict the chemical shifts. Well, the structure elucidation piece for molecular structure determination, that the holy grail that Dean was referring to, is just switching those. You take the chemical shifts and you put that in as your input data and you see if you can predict the distances between the atoms. From a machine learning point of view, it's that simple. From a mathematics point of view, it's a bit of a problem because you've got 20 carbon chemical shifts and 500 internuclear distances for a molecule of sensible size. And therefore you need more NMR data. You need the carbon chemical shifts and the proton chemical shifts. You need the coupling constants. You need the coupling constants between atoms that are 6 and 7 and 8 bonds away, in theory. And so this is something that we've actually just started doing. I did have another slide on a different approach to doing this that I was going to use that was literally so last month, because 2 days ago, we tried this for the first time, and it should have a picture of Ben up there in the corner as well. Ben did this the other day, and for molecules with less than, so very small molecules, 6 heavy atoms in them, it was getting the right structure more than 50% of the time when you just fed it the NMR data and got it to predict the distances between atoms. Now, I'll caveat that because it's absolutely the holy grail. It's absolutely black magic that this works and that it works so often. And the reason it works so often is we gave it all the NMR data. Every single coupling constant in the molecule, all the carbon-carbon one-bond couplings are in there. And if it can't work out these two things are bonded because they've got a carbon-carbon one-bond coupling of 50 hertz or whatever, then it's probably doing something wrong. So it's not that this is the solution and we've solved everything. It's actually that from a machine learning point of view, this is perfectly legitimate and perfectly possible to do. The question becomes, can you do it from experimentally valid NMR data that you could actually measure in NMR? And so for us, it's really about how much NMR data we can measure, how accurately we can measure it, and then we've got a machine that can churn out the structure straight from that. So that's where we are now. I think the next slide is the people who did this. Yep, so DFT levels of accuracy in milliseconds, stereo isomerism comes as standard, car salesman, chemical shifts, scalar couplings, we can even do Mulliken charges and other atomic and molecular properties. And trying to predict the structure from the spectrum is where pretty much all the people on the slide are now working, well, except Will, who's at the top, because he's now earning more money than I do doing machine learning in industry. So I will leave it there.
Oh, great. Thank you, Craig. Thank you. All right. So we are moving to the Q&A session, and I would suggest the people who are listening there and to unmute yourself, then introduce yourself, and then and ask your question to any member of the panel. So we would know that who is referring to. So I'm open the chat, and I don't see any questions in the chat. So we will take any questions live, and I hope that the people are capable to unmute themselves. Krish, are we in that kind of stage of the Zoom? But
yes, everyone can unmute themselves and ask directly.
Perfect. Yeah, but first of all, thank you, Dean, thank you, Craig, and thank you, Ryan, for very, very nice presentations. I think it's a very nice overview of the current state of the DFT, where we are, the limitations, and actually, yeah, where we want to go, and what are the critical points, and where the challenges are, where the gaps are. That's where our science is going to. So. And it seems like we are on the same page. Yeah, I see a lot of things that we have been thinking about.
So Dean, actually, I've got a couple of answers for your questions that you put up there. They're not good answers. I've just got answers. But you asked about how you get so the calculation of NMR properties is actually a kind of semi-solved problem, if you like, with DFT. We can do it reasonably accurately. Getting the right 3D geometry is a solved problem. The hard bit is getting the energy and therefore the population of conformers if you've got more than one conformer. And your solution around reweighting it, so getting it to do a best fit of the NMR data you've got to the structures, I think that's half of the right solution. So reweighting has to be done using some independent parameter. And for me, for example, if you use the coupling constants to reweight the populations, but then you keep the chemical shifts aside, they haven't been used, and then you can test the answer with those. It's not a very good answer because coupling constants are conformationally sensitive, chemical shifts are okay, but we did this a few years ago with biomolecules in 2017, and we did it with NOEs. We reweighted with NOEs and then tested the new weights against, or the new populations, against coupling constant. And so both are conformationally aware, and the answer got better. The coupling constant errors went down once we reweighted it using NOE data. So that was very reassuring that you use one set of data and then test it against an independent set.
Yeah, that's a good point.
We have a question in the chat from Neil. So he writes, hi, Craig, excellent presentation. Do you have any plans to use noisy data to include through space coupling as well as through bond couplings?
Yeah. So yeah, that's a really good question, and we don't particularly have plans to do it because actually what the workflow that people have described already gives us to you for free. If you take a NOSI spectrum or NOSI data and convert it into internuclear distances using the standard sort of panic and R to the -6 kind of approaches, and if you don't know what I'm talking about there, you're welcome to go and look up our papers on it. Krish loves panic. Krish panics a lot. That allows you to take the peak intensities in a NOSI, convert them into numbers that represent a time averaged distance between those nuclei, but time averaged with distance to the power of -6, because that's the NOE relationship. And therefore, if you've got all of the conformers of a molecule with all of the distances calculated already, then you can take those conformers and their expected populations, predict what their NOE distance would be given that weighted set of conformers, and compare that to the experimentally measured NOE distance, and it should fit within a few percent. And so we calibrated this on a good day with strychnine, which is rigid and never does anything else. Then you should get an error of about 3 or 4%. If it's in DMSO and a bit sludgy and lots of conformers, the errors will probably be a little bit higher. But yes, you can use NOEs as a constraint in order to get the conformational stuff out, rather than as a predicted thing, because NOEs is a geometrically derived value, not a quantum mechanical property per se.
Oh, here you
If
go.
if I may continue on that question, many years ago this is the kind of using populations to calculate time average or weighted average distances or spectra or has been there was a publication way back 20 years ago or something like that on VCD. That's a very popular way to get both using circular dichromosome, vibrational circular dichromosome to generate what would have been the population ratios of different conformers, for example, based upon observed VCD experiment and calculated of multiple conformations. So that's something which I am quite impressed that we are getting into that area in NMR.
So with VCD or with any method where you can calculate a spectroscopic response, and so VCD is one of those, then the DFT output file has the numbers in it. And all we actually do when we create a data set for impression is we just pull numbers straight out of the DFT file. So instead of telling it to look at the chemical shifts, we can tell it to look at the VCD numbers, whatever those are. I've never done them, so I don't know what numbers they are. But in principle, yeah, and the problem with VCD is you have to use DFT and therefore it's slow. We could train an impression machine to do that really fast. That would be cool. We can just add it in as another parameter.
The question came for Dean and Craig. So this is related to the Neil question. Sorry, this is a question from the Rolf Adams. Sorry, I'm on the tram, so can't ask. So, you're spoken about chemical shifts and verifying structure with those. Are they accurate enough yet to ignore the noisy data now?
Can I answer this first so that I can challenge Craig to see?
Okay.
So I think yes. So for a long time ago, we, for example, had a terpene that was just a polycyclic hydrocarbon with multiple conformations, and we looked at on the order of 20 diastereomers of a hydrocarbon, a big ball of grease, and you could pick out the correct one using DFT computed chemical shifts, and we used Jonathan Goodman's statistical analysis to help us and whatnot. Yeah, it was just DP4 with nothing after it at the time. And so Craig, I'm wondering in your approach, is it good enough for that? So, systematic errors are useful. Well, I guess what I'm really asking you is your error distribution reflective of systematic errors, or are they not so systematic?
I don't think it needs to be systematic errors. It needs to be normally distributed errors, or T-distributed, or whatever it was that Jonathan used for DP4. So that error graph of DFT versus experiment has a particular shape, and all that DP4 does is says, do the predictions for this molecule fit reasonably within that shape, or are some of them too many even outside it? And our distribution looks like their distribution. So the answer is yes, in theory, as long as there's not the extreme egregious outliers like an allene or something like that. And so where it just gets something completely and utterly wrong, DP4 will fail when it's based on DFT that's completely utterly wrong, and it would fail if it's based on impression that's completely utterly wrong. So the question is, how often does impression get it wrong when DFT doesn't, I guess is the only part there. But yeah, DP4 is something we absolutely, it's on the list of things we have to do. Jonathan and I keep talking about it, saying really must do this. I'm getting enough students working on this now that I think I can just send them up to Cambridge and they can sit down and recalibrate DP4 using impression. It just requires a data set which DP4 has. So you just recalculate that data set using impression, recalibrate it, and then it should in principle go. And then you have to test it against known systems. And so I've got a whole set of, Alexei, can I have dicotomol, please? Then quatolide and echinopene, and cleosphenol A as well. We just need the experimental data and then all the diastereomers, and we can go through and do the impression predictions and see if we get the right answers, which will be a very cool test.
You can get them from our paper. I think it is all there.
Too much like hard work.
I have a question to you, Craig. It's something which is I want to understand more. So the case program is predicting chemical shifts based on this empirical, and one of the one of the methods of the prediction of the chemical shift is based on the neural network, which is essentially ML trained on the experimental data. And my experience with the predictions of the neural network, that they're quite often off, even from the data which are predicted by the host. No, I'm not talking about even DFT. So my question to you, Beck, is have you considered to train your system not on the DFT data, but on experimental data? And if you try, maybe you failed again, and maybe do you have an explanation? So I'm just curious to know.
Yeah, so there's a number of reasons why we use DFT instead of experiment. The primary one is we're interested in 3D structure, and experimental data is rubbish for 3D structure. The protons are misassigned. Diastereotopic protons are reported as a range rather than as two separate chemical shifts. And if they're reported as two separate chemical shifts, they're probably misassigned the wrong way around. So experimental data is really, really hard to encode properly. So when you go into the literature, it's just wrong. And it's either wrong or they don't include the assignments in a way that's helpful. So that's one part of it. The second part of it is that with DFT, there's a direct relationship between the 3D structure and the NMR data, the predicted NMR data. And impression takes a 3D structure and gives you the NMR predictions for that one 3D structure. Experimental data is a time average of all the conformers, and therefore there's not a correspondence between experimental data and a single 3D geometry. In fact, it's some smooshed up ensemble of 3D structures. And so if, for example, you want to predict experimental coupling constants, you can't, because there's no one 3D structure that corresponds to those experimental coupling constants except in rigid molecules.
Mm-hmm.
The flip side of this is that you can train a machine like we've done on DFT data to get it really good at predicting chemical shifts, except for the experimentally variable bits, the ionizable groups, the solvent effects, the temperature effects, all those kind of things. And then you give it experimental data for rigid molecules that are measured under different pHs, different solvents, whatever it might be, and you bolt that on to the end of your prediction. So you take your DFT predictions and correct them to give them a match to experiment. And that's the solution to the ionizable groups question that Dean was asking, is you train a machine to correct DFT or to correct impression in order to make it learn about ionization, about hydrogen bonding, about whatever it might be. That's the approach that we think you need to take, but it requires really good experimental data.
I was going to say, I think you need the data, yeah.
Yeah, that's, well, yeah, it's also the solvent, the experimental data in the very different solvents. So
But the nice thing about doing that transfer learning is you probably only need 100 molecules, as long as they're diverse, structurally diverse molecules that give you OHs and NHs and amides and carboxylic acids and things like that. And then you can run those 100 molecules in 10 different solvents, but you don't need every molecule in every solvent because it learns the correlations between, or the patterns between it. You do them at 5 different temperatures, but not every molecule at every temperature in every solvent. And so you probably need on the order of about 5,000 experimental data points, or 5,000 NMR spectra, all of which have to be assigned perfectly, no mistakes. And so that's why we've avoided experimental, but correcting DFT to experiment is easier than just training the machine on experiment, because you can do it on a smaller data set. To train our whole machine takes 25,000 molecules plus. You can probably do it with fewer molecules if you're doing the transfer learnings.
There are more questions. People can unmute and ask the questions now instead of chatting, writing it in chat box. Please go ahead.
There is a question, Craig, again to you from Saddam. Is there any open source? Is it an impression? Is it an open source software or code on GitHub?
It's not open. It's not open source yet. It's on our GitHub. So Kelvin, in about a month's time, is starting a project. He got funding for a year. He bid for it himself and got awarded the funding to develop it into a deployable piece of software. And it'll be available on a browser base, so very similar to Cascade, basically for academic use, because that's what academics want, is a nice, easy website they can go to. But then also a deployable version that can be packaged up and put into something where I'm guessing, Alexei, that you guys don't want to upload your commercially sensitive molecules onto a Bristol academics website. I figured you wouldn't. So this deployable package could be installed locally, and you could then use that. So hopefully that'll be coming. The website will come first. So we're looking that this would become available in the future.
You show this interaction with how you submit the sample as a smile, as small molecule as a smile, then calculate the chemical shifts in the real time. Is there any limit for the number of atoms you have?
Yes, no, maybe. It literally depends on the RAM on the computer you're running it on. So it's part of the thing that Kelvin's going to try and solve. If we host it on the cloud, then it comes down to how much RAM you're prepared to pay for on the cloud, how much CPU power you're prepared to pay for, and so on. But yes, however, it batches up the molecules. And so one molecule, it can probably be 10, 20,000, and it would be okay. But if you want to run 1,000 molecules, each of which has 100 atoms, then it will batch them up into groups of 10 and 20 and do them like that. So it'll do 20 and then upload the next 10. So it's just RAM limited. Yeah.
Alexei, there's some more questions in the chat.
Okay, below. Above? Oh, yeah. Okay, let's see. We paused that. Okay, there is this question, I didn't read it. Hello, this is for Salim again. Thank you all for your excellent works. My question goes to Dean Tantillo. Do you do your shift predictions and experimental shift determination on crystal structure? Can I also notice a wide deviation for chemical shift environments attached to heteroatoms like oxygen and nitrogen? What is the reason for that? It's a lot of questions, Dean, maybe one by one.
I can read them. So yeah, so I'm not sure I understand the question about the crystal structures, but the experimental shifts, we take them from literature papers and they're all in solution. And if there is a crystal structure available, then that's always good confirmation of the structure. Of course, if you're trying to reproduce a proton on a heteroatom, well, that's super solvent dependent. If you're having trouble with carbons, or especially protons on one atom away from a heteroatom, that's probably also a solvent sensitive issue. There might be some CH hydrogen bonding with the solvent or something. It's a linear scaling approach. And then the last question was about groups undergoing fast dynamics on the NMR timescale. If things are interconverting on the NMR timescale, you just average them in your prediction. So those are all very practical things, and actually they're all I think they're all mentioned in that chapter I pointed to, where we kind of go through all those sort of issues when you're actually doing your calculations. So hopefully I covered everything there. Yeah, some of the most annoying things I'll say about again, ionizable groups, alkaloids, protons, near amines are a real pain, if whether or not the amine is protonated, and then sometimes there's internal CH something hydrogen bonding within the molecule and so forth. So that's certainly a problem. And the context in which I got interested in this was some of my total synthesis friends would synthesize a natural product, and it would be the correct structure. They know what they made, but their spectrum didn't quite match the reported spectrum in the literature, and it was probably the result of acid content or concentration, and they were never quite able to get an exact match. And we thought, well, maybe we could just predict, at a range and show that at some value you get the right match, and it never quite worked out. So, because then the referees on those papers tell them, well, you have to wait until you get a crystal structure. So I've already told you how synthetic folks can be.
The ionizable group thing, if you've got a carboxylic acid and the carboxylate and you don't know which one it is, you can of course calculate both. Yes. And you treat it as a population problem. How much percentage have I got one and the other?
Yes.
The problem is Yeah, I know, and it doesn't work either, does it?
Well, part of the problem is those in particular like to hydrogen bond to each other as well, but sometimes it works just fine. And if you were doing your own experiments, you could probably resolve that. But if you're stuck with some experiment in the literature from 20 years ago and you just want to know if the structure was right, that's a different problem. So
yeah. And the reason that it doesn't work well, I think, is that DFT is calculated in a box in a computer. So it's a molecule with nothing around it. And so anything that the molecular structure generates, so any effect the molecular structure generates can be taken account of in a DFT structure. Anything that's a specific interaction with solvent, like a hydrogen bond to or from the solvent, cannot be taken into account in a DFT no matter what you do. So if you can't calculate a carboxylate, you've got no hope unless you put it in a box of solvent.
Yeah, we have tried adding explicit solvent molecules, especially in like for amines and ammonium ions, and then if you immediately have the problem of where to put them and how many to put, and then configurational sampling is worse than conformational sampling, and so yes.
You got it.
Yep.
Yeah, and there's no software in the world that doesn't, which is really annoying.
Actually, we also have some experience over calculating the ionized molecule amines, ionized amines. It actually is relatively accurate predictions. And also on the last ENC conference, it was a presentation. The same theme was that if you just protonate and calculate in Gaussian as a charge with a charge, it will give a very nice predictions for the carbon chemical shifts. And I think it's in the nitrogen who has been involved. What we found that it's if you put the counter ion for that, so you want a neutral, then the whole effect disappears and the chemical shifts bad again. So it seems like this counter ion is a bad thing.
You're exactly right. I was just going to mention that it totally depends on the counter ion too. We played a bit with that. So yeah. Which of course the solvation of the counter ion is a big issue.
Exactly.
Yeah. In fact, you mentioned that the dimerization of a carboxylic acid is basically it's the same problem. It's interacting with some other molecule that isn't represented in the DFT calculation. And if you represent it like a counter ion and just leave a counter ion and the cation and the anion together, that's not a real representation of two things in solution that are dynamically moving closer and further apart and so on. So yeah, it's reproducing the experimental conditions that's the hard bit, not the actual quality of the quantum mechanical calculation itself.
Correct. I agree.
Well, let's move. There are a couple of questions in the chat. So this is from Tim Claridge comes. As noted already, one of the bottlenecks in using DFT is the time requirements for accurate geometry optimization. So I was intrigued by the suggestion of using just XTB geometries. What are the panel's thoughts on this as a general approach prior to DFT NMR calculations, which are quicker?
I would challenge Ryan on this.
Yeah, so although I never tested XTB for geometries, we did test other semi-empirical methods, and certainly the accuracy goes down quite a bit. So I think one of the areas we were trying to get into was just in density fitting for GGAs, because that will help, since the basis set size is like, a big factor in terms of the time requirement for DFT. So yeah, but I think it would be interesting. I think especially the Orca suite, software suite has some couple, semi-empirical version, a couple cluster, which we haven't tried. So I guess some of those type of things would be interesting to feed it some geometries and try to speed it up in that way. But so far I haven't seen anything personally where I felt the results were worth it.
Yeah, maybe before Craig, I'll just say that XDB is certainly fast, and there Crest has built into it ways to sample things, and we do a lot of things that aren't NMR, and we use that for conformational sampling in a lot of different contexts, and it's kind of our go-to first step, but we're always super cautious, and it messes up more frequently than you would hope. But for CHNO and maybe F for routine molecules, it might be okay, right? As you showed in some of your stuff, Craig, it might not make a big difference, but for beyond that, or if you have like particularly unusual molecules, then you really need to check. So it always depends on the molecule you care about.
Yeah, I'd give the glass half full answer, which is that, Ryan, can you check? Because I think the geometries it gives are very good reproductions of DFT, but they're not astoundingly good reproductions of DFT. So turn that around. If you then take those geometries, the XTB geometries, and try to run a DFT calculation on them, I think they'll probably not do well, because DFT cares about electrons, and electrons care about exactly the positions and the angles and every little detail. So if you change the angle between two protons, a CH2 group, from about 104 degrees to about 112 degrees, just doing that on it, the coupling constant goes absolutely nuts. It changes by about 5 or 10 hertz or something like this. It goes from positive to negative and all sorts of stupid stuff. And so if the XTB's a good approximation but not quite there, then DFT is going to notice. Our machine learning system doesn't care, because it doesn't do electrons, it doesn't do orbitals, it just looks at really something about geometry. And presumably, from what we've seen, it doesn't care if it's 1.54 angstroms or 1.53 angstroms. That doesn't bother it. 109 degrees versus 107 degrees. That's not something that our machine learning system cares about. It's not important enough for the NMR properties. But when you put it through DFT, it probably does care, because the electron distributions will go nuts.
I want to add for this empirical or ML-based geometry optimization. So one of the software that we use internally is called ANI. It comes from the Rödberg group. And it's actually, I was really, so I checked did a benchmarking of the geometries with the DFT calculations. It's after the chemical shifts, proton and carbon chemical shifts, it has a slightly different scaling factors, but the accuracy is almost the same as DFT. It's very difficult to even differentiate one from another. It tells me that the geometry is pretty close. Well, the only caveat, it has been the databases, the molecular basis, the set that we used was very rigid. So, and when its flexibility comes in, probably it is not as good. But for the rigid molecules, it's almost the best. And the speed is it's like a molecular mechanics. So it is
Well, that's really good to know. That's really useful.
Yeah, there is another question comes from Saddam. It's Dr. Craig, how does impression perform for structures attached to transition metals? Taking care of the relativistic effects. That's the second subset.
I don't know. We've never tested it, but I can tell you the answer. Rubbish. Absolutely rubbish. It'll be terrible, because it's never seen them. So when we trained generation 1, and it had only seen carbon, hydrogen, nitrogen, oxygen, fluorine, Will came into the lab one day and he said, I've got a real problem with purple. I said, what the heck do you mean by you've got a problem with purple? And he goes, well, purple, whenever there's purple in the molecule. I said, what do you mean by purple? He was a physicist. He didn't know what a methyl group was when he started his PhD. So, he said, I've done that thing where I look at the data. You told me to look at the data. I've looked at the molecules and I've got purple in them. And he brought it up and said, oh, you mean phosphorus? And he was testing it on a molecule that had phosphorus in it, and the machine had never seen phosphorus. It came up with a carbon chemical shift of about 400 ppm or something ridiculous like that. So machine learning, if it doesn't know about that system, it will go nuts. And we've not trained it on metals because the DFT calculations are non-trivial. But yeah, machine learning will be rubbish at anything it's not seen before. If you don't show it a horse, it cannot recognize a horse. It'll tell you it's a cat or a flower. Or Pinocchio.
And so it was another sub question, relativistic effects, but I think you touched on that it's difficult to, right?
So impression's as good as the DFT. If you've got DFT that takes some relativistic effects into account and you put that into your training set, then you can train it. You could also train a transfer learning system to correct DFT for relativistic effects. So we could give it a set of 100 molecules with bromine in it that have been relativistic corrected, and it can then learn the correction factors from that. Good to see that Ralph's finished his tram trip in Manchester.
Okay, guys.
Are there any other questions?
Can I just quickly?
Oh, another question comes.
Can I just thank Krish for recommending to me that I drink wine during my talk? So it made it much easier.
Very good. Very good. You were disappointing me when you came into the meeting. Now I am pleased. Okay, so I think we are actually reaching a point where this particular workshop is competing for the top rating in terms of total amount of time. People are waiting to sit there and then watch, listen, and all that, which is very good. I am very, very pleased with that. And personally, I am really impressed with how computational approaches is going so fast, improving so fast. The only downside of that is it makes me feel older than I actually am. Beyond that, I think I'm very, very pleased. I want to alert not only this team but also the everyone else who is listening. One of the Ivan's vision is to give practical information as well. So if you have software, freeware, or whatever that you want to show, we can definitely arrange tutorial type of similar meetings. We have done that with other vendor softwares, but this is something perfectly acceptable. This is within the scope of Ivan. So I would be very glad to entertain that ideas. In general, I like to entertain ideas from anyone who has some ideas what we can do more. Next month, I want to thank Alexei and the team for a wonderful, wonderful presentation today, workshop today.
Thank you.
I want to alert everyone, next month is quote unquote introduction to imaging and localized spectroscopy based application of NMR, which is, I am excited to listen to that. So watch your email and register and support us in this continuing endeavor. After that, I want to thank everyone. Any other questions? The poll is open right now. If anybody has questions, comments, do so right now if you want.
I just want to say, thank you, Krish, and the team. Yeah, thank you for giving us the opportunity to to share our knowledge and spread the good news about DFT.
Yes, of course.
Thank you.
I'm very glad that we were able to swing this in eventually. I have been talking to you for a while, but eventually we were able to break it. Yeah, so I'm glad. Thank you.
Thank you.
Thank you. And I think with that, let us close this meeting and see you guys all next month.
Cheers all.
Bye-bye.
Bye-bye.
Bye, everyone.